Imagine you are trying to simulate the universe.
Oh, wow. Starting big today.
Right. But seriously, think about it. Not just like a simplistic rendering, but a true physical simulation of reality at the actual Planck scale.
That is a massive computational ask.
It really is. You would need a computing architecture that doesn't just crunch numbers, but fundamentally mirrors the discrete, interconnected fabric of space-time itself.
Right. You'd need the hardware to match the physics.
Exactly. And if you build a machine that perfectly mimics the underlying mathematics of reality, you have to ask yourself a somewhat terrifying question. Are you just building a computer, or are you actually engineering a miniature universe in a lab?
I mean, it sounds like the setup to a speculative sci-fi novel, but this is the genuine philosophical territory we find ourselves in today.
It really is. Welcome to the deep dive. Today we are looking into a white paper that proposes an architecture called the Quantum Lattice.
And to be clear with everyone listening, this document is a wild ride.
It is, it's definitely something else. Because it begins as this highly grounded, heavily technical hardware schematic for a monolithic, all-carbon quantum processor, right?
Right. It details how to manufacture what they call a zero-fab quantum computer using lasers and aerogel.
Which is fascinating on its own. But then, halfway through its technical specifications, the document just completely pivots.
Yeah, they take the exact mathematical framework they use to design their quantum hardware and apply it to cosmology.
Right, proposing that gravity and black holes are simply emergent properties of a discrete information lattice.
It is a profound synthesis, really.
Mm-hmm.
We have a whole suite of source materials today, including the core architectural white paper, specific quad-tip simulation results for the qubit dynamics.
All the heavy math.
Yeah, and the theoretical physics proofs that attempt to bridge quantum error correction with general relativity.
So to appreciate just how radical the hardware side of this proposal is, we need to consider the current state of quantum computing right now in 2026.
Well, if you look at the industry leaders, companies like Google with their 105 qubit Willow chip, or IBM's Heron processor,
Right.
they rely heavily on superconducting transmon technology.
And the standard approach there for the past decade, really, has been this additive multi-material architecture, hasn't it?
Exactly. You start with a silicon or sapphire substrate. Then you deposit layers of superconducting metals.
Usually niobium or aluminum, right?
Right. You etch in your circuitry, you add dielectric layers for insulation, and you rely on Josephson junctions to create the nonlinearity required for a qubit.
And because you are dealing with these incredibly sensitive superconducting states, you have to house the entire assembly inside a massive dilution refrigerator.
Yeah, the giant gold chandeliers you see in the press photos.
Exactly. You're chilling the chip down to about 15 millikelvin just to prevent thermal noise from destroying the quantum states.
But that extreme cryogenic requirement is just one part of the challenge. The deeper physical issue with the transmon approach is the heterogeneous nature of the materials themselves.
Meaning they're using too many different parts.
Basically, yeah. Every time you bond aluminum to silicon or introduce a dielectric oxide layer, you create a material interface.
And from a quantum perspective, an interface is just a chaotic boundary zone. You end up with dangling chemical bonds and trapped charges.
Right, and those trapped charges are the primary source of two-level system noise, or TLS.
Which is awful for coherence.
It's terrible. The heterogeneous structure essentially acts like an antenna for stray electromagnetic fields and phonon vibrations.
So it's an inherently noisy environment.
Very much so. It requires massive overhead just to keep the qubits coherent for a few hundred microseconds.
Which makes the quantum lattice proposition so compelling for you as the listener. The authors look at that multi-material, cryogenic, heterogeneous stack, and they just abandon it entirely.
Yep. They propose a monolithic architecture. No silicon, no aluminum, no complex oxide layers, just carbon.
A single element paradigm. I was trying to conceptualize how much of a departure this is.
It's massive.
The standard transmon approach is like building a complex machine out of disparate Lego bricks. You have plastic snapping into metal, gears grinding against axles.
The interfaces are where all the friction happens.
Exactly. The quantum lattice, by contrast, is more like a sculpture carved out of a single flawless block of diamond. But in this case, the block isn't diamond.
No, it's a highly engineered graphene aerogel.
So let's break down the physical characteristics of this quantum sponge, because the density figures in the paper are striking.
They really are. They quote a density between 0.01 and 0.1 grams per cubic centimeter.
Just to ground that in reality for you, the lower bound of that density range makes the aerogel significantly lighter than the ambient air in the room you are sitting in right now.
Wait, really? Lighter than air?
Yeah. Yet, because of the covalently bonded carbon matrix, it retains immense structural rigidity.
That's wild. But the trick seems to lie in the porosity, right? The structure is permeated with these air-filled nanopores ranging from 10 to 100 nanometers.
Right. And in a traditional chip, engineers have to meticulously deposit dielectric materials insulators to prevent crosstalk between neighboring quantum components.
But here, the void spaces themselves act as the dielectric spacers.
You achieve physical and electrical isolation natively. No foreign materials causing TLS noise.
And those nanopores also solve the thermal management problem. The thermal conductivity of this aerogel is exceptionally low.
Like, how low are we talking?
The paper lists it at 0.005 to 0.03 watts per meter Kelvin.
Which is a massive drop compared to a standard graphene sheet. Standard graphene conducts heat incredibly well, doesn't it?
Oh, natively, graphene is an exceptional thermal conductor. But when you construct it into a sparse, porous 3D web, heat simply doesn't have a clean, continuous lattice path to travel along.
So the phonons, the acoustic vibrations that carry thermal energy, that just get lost.
Basically, yeah. They scatter endlessly within the chaotic porous geometry. So by damping out the phonons so aggressively, the aerogel creates an acoustically and thermally dead environment.
A perfectly quiet acoustic house for the qubits to live in. But the physical structure is only half the battle, right?
True.
Because the white paper is hyperfixated on the chemical purity of the carbon itself. They specify the absolute necessity of utilizing a pure carbon-12 environment to suppress the noise floor.
And the isotopic purity is critical there because of how typical semiconductor qubits fail.
Right.
You look at spin qubits in silicon or gallium arsenide, their primary decoherence mechanism is hyperfine-driven dephasing.
Right, which is the interaction between the electron spin of the qubit and the nuclear spin of the surrounding host atom.
Yes, most isotopes possess a nuclear magnetic moment. So if your qubit is surrounded by atoms with non-zero nuclear spin, those nuclei create this fluctuating magnetic bath.
And the electron spin becomes entangled with this bath, and your quantum information just leaks out into the environment.
Exactly. But carbon-12 bypasses this entirely because it has a spin-zero nucleus. It is magnetically inert.
The surrounding lattice doesn't interfere with the qubit because it mathematically cannot couple with it magnetically.
It creates a true spin vacuum.
But this is where I hit a massive stumbling block while analyzing the source material.
What did you find?
Well, the authors casually state that natural carbon is 98.9% carbon-12, and therefore an isotopically purified carbon-12 aerogel eliminates hyperfine dephasing.
Right.
But they skip over a glaring industrial reality. That remaining 1.1% of natural carbon is carbon-13, which absolutely has a nuclear spin.
I see where you're going with this.
Right. Purifying carbon to a strict 100% carbon-12 on a commercial scale is practically a Manhattan Project-level logistical hurdle.
That is a highly valid critique of the roadmap. The white paper treats isotopic purification as a solved prerequisite, focusing entirely on the physics of the resultant matrix.
It feels akin to assuming a frictionless vacuum for a high school physics equation. The techniques required to strip out that 1.1% of carbon-13, whether through chemical vapor deposition with isotopically pure methane or gas centrifugation, are astronomically expensive.
And they yield tiny quantities. The supply chain bottleneck is undeniable. If you require absolute isotopic purity to achieve the stated coherence times, you are basically trading the cost of running a massive dilution refrigerator for the cost of running a specialized isotope enrichment facility.
Yeah, you're just moving the bottleneck somewhere else. But assuming they can secure this perfect 100% carbon-12 precursor, the environment they're building is mathematically pristine.
Right. We have a thermally isolated, magnetically inert sponge.
Which allows us to look at the quantum tenants actually living inside this sponge, the qubits themselves.
And these depart radically from the superconducting circuits IBM and Google use.
Radically. They are utilizing 3 to 5 nanometer graphene quantum dots, or GQDs, which operate on a hybrid spin valley charge mechanism.
Coupling 3 degrees of freedom into a single 5 nanometer dot.
It's incredible. Let's unpack the mechanics of this, starting with the valley index. When the paper refers to a valley, it's mapping the momentum space of the carbon electrons, correct?
Yes, exactly. We have to look at the Brillouin zone of the graphene lattice. Because of the hexagonal honeycomb structure of carbon, the energy momentum mapping of the electrons produces a landscape with two distinct degenerate energy minima.
And these are the K and K prime valleys.
Right. An electron in the lattice will settle into one of these two valleys. And because they are widely separated in momentum space, an electron cannot easily jump from the K valley to the K prime valley.
It requires a massive momentum transfer, usually a short wavelength phonon collision, right, just to kick it across.
Exactly. And since we've already established that the aerogel structure brutally suppresses phonon propagation,
the likelihood of an electron accidentally scattering between valleys is practically minuscule.
yeah. The source data shows that in bilayer graphene quantum dots, the valley relaxation time, the T1 time, can easily exceed 500 milliseconds.
Wait, half a second of stability.
Half a second.
That is a geological era in quantum computing timelines. Most systems struggle to hit a few hundred microseconds.
I know. But they don't even stop at the valley index. They couple it directly to the electron spin to create topological armor.
The spin-valley locking mechanism. So carbon is a light element, meaning its intrinsic spin-orbit coupling is relatively weak compared to heavier semiconductors, right?
It is. But in the specific geometry of bilayer graphene, this weak coupling interacts with the valley degree of freedom to create what are known as Kramer's pairs.
Kramer's pairs, right. Kramer's degeneracy essentially dictates that every energy state has a time-reversed partner with the exact same energy. The spin and the valley index become entangled into a single protected state.
And the beauty of a Kramer's pair is its resilience against first-order perturbations. Environmental noise typically acts on 1 degree of freedom at a time.
Like a stray electric field might nudge the charge.
Right, or a magnetic fluctuation might nudge the spin. But to break a Kramer's pair, the noise has to act on both the spin and the valley simultaneously with precise phase alignment.
So the environment is forced to perform a highly complex, coordinated attack just to cause a single error.
Exactly. And because the aerogel has already stripped away the thermal and magnetic noise, the topological protection is overwhelmingly effective.
The simulation data in the paper points to potential relaxation times of 38 seconds at 30 millikelvin.
38 seconds.
A 38-second T1 time fundamentally alters the algorithmic possibilities of the machine. It's almost hard to wrap your head around.
It is. But that supreme isolation creates a secondary engineering problem.
Right. If the data is so heavily armored against the environment, how do you intentionally write to it?
You have to temporarily lower the topological drawbridge. And the authors achieve this using the charge tuning mechanism.
Which involves those laser graphitized struts within the aerogel, right?
Yeah. The dense walls of the carbon pores act as electrostatic gates. By pulsing a specific voltage through these struts, they can alter the local electric field around the quantum dot.
This is beautifully illustrated in the QuadEB simulation data provided in the sources, specifically the Hamiltonian modeling of the Qubits energy levels.
Oh, the avoided crossings chart.
Yes. Looking at the data for the avoided crossings gives a very clear picture of this. The simulation maps the energy levels as a function of the applied gate voltage, which they label V superscript G.
Right. And when the gate voltage is 0, the lines representing the spin valley states cross perfectly. The states are entirely degenerate and locked.
But when they ramp the voltage to V superscript G equals 0.8 times delta 0, where delta 0 is the spin orbit splitting the geometry of the energy landscape warps.
The states no longer cross. They repel each other, creating an operational window.
That avoided crossing is where the magic happens. By tuning the voltage to that exact point, you force the qubit out of its protected state just enough to allow a charge-mediated interaction.
And they actually map this interaction in the 2-qubit dynamic simulation, tracking a swap gate between adjacent GQDs.
And the state transfer is incredibly fast. The population swap occurs in 3.1 nanoseconds.
Think about that. If we contextualize that against the 38-second coherence time, the ratio of gate speed to coherence time is staggering.
You could theoretically execute billions of gate operations before the physical qubit naturally decays.
And the simulation validates a gate fidelity greater than 99%, driven largely by the suppression of local charge noise.
Which is huge, because in standard planar semiconductor architectures, charge noise typically hovers around 0.06 to 0.10 gigahertz, dragging fidelity down into the low 90s.
Right. But the aerogel isolation pulls that noise floor down to less than 0.02 gigahertz.
It's brilliant, but even at 99% fidelity, you are still going to accumulate errors over a long enough computation.
You always do.
Which brings us to perhaps the most elegant engineering solution in the entire white paper, how they handle error correction, and the dreaded wiring bottleneck.
Ah, the wiring bottleneck. That is the silent killer of quantum scalability.
Definitely. For you listening, if you look at standard cryogenic systems, the physical infrastructure scales linearly and sometimes exponentially with the qubit count.
Right, because to execute active error correction on a superconducting chip, you have to read the syndrome of a physical qubit.
And that signal has a long way to travel. It goes from the 15 millikelvin chip, up a physical coaxial cable, through multiple thermal isolation stages out of the cryostat, and into a rack of classical servers operating at room temperature.
The server calculates the parity check, determines the error, and then has to send a corrective microwave pulse back down an entirely different cable.
The latency of that round trip is a major issue, sure, but the physical mass of the cables is the true hard limit.
Yeah, coaxial cables conduct heat. If you try to run 10,000 cables into a dilution refrigerator, the passive heat leak alone will overwhelm the cooling power of the cryostat.
The system will undergo thermal runaway. It just physically can't scale.
But the quantum lattice circumvents this by moving the classical processing directly into the cryostat. It's baked into the very same carbon matrix as the qubits.
That blew my mind. The paper details how peripheral zones of the aerogel are graphitized into classical graphene field effect transistors, or FETs, and carbon-based memristors.
It is a true system on a chip, a hybrid quantum classical architecture, where the control plane is physically interwoven with the quantum plane.
The memristors are absolutely fascinating here. They act as localized, non-volatile analog memory. They can perform real-time syndrome extraction locally, logging phase slips or bit flips without needing to communicate with an external server.
And once the memristor flags an error, the adjacent graphene FET layer calculates the necessary correction and fires the localized electrostatic pulse directly to the graphitized control struts we discussed earlier.
The correction loop happens on the scale of micrometers, entirely within the cold stage of the system.
Zero latency and zero physical cables bridging the temperature gradient.
Which is incredible, and this local in-matrix processing allows them to implement a highly specific error correction protocol called Quantum Low-Density Parity Check Codes, or qLDPC.
And that's a big shift, because standard industry roadmaps generally rely on surface codes for error correction.
Right, and surface codes are two-dimensional, relying on nearest neighbor interactions.
But their topological efficiency is incredibly poor. To create a single, reliable logical qubit using surface codes, you often need a massive array of physical qubits acting as stabilizers.
Sometimes a ratio of 1,000 physical qubits to one logical qubit.
The hardware overhead just becomes insurmountable if your goal is millions of logical qubits. But qLDPC codes allow for non-local parity checks.
Because the quantum lattice is natively three-dimensional, and the in-matrix FETs can route classical data across the structure instantly, they can implement highly connected bipartite graphs.
The mathematical efficiency of qLDPC allows physical qubits to participate in multiple stabilizer checks simultaneously.
And the white paper calculates that this specific 3D architecture reduces the hardware overhead required for fault tolerance by roughly 90% compared to a planar surface code.
90% is a massive reduction.
Yeah.
And the simulation of the 100 syndrome rounds is the empirical backing for this claim.
Let's talk about that simulation. They modeled a 4 physical qubit plaquette and subjected it to a punishing 1% physical error rate per gate over consecutive cycles.
Right.
Without the local FET correction firing, the qubit state collapses almost immediately. By round 100, the fidelity of the uncorrected state degrades to 36.6%.
It's completely randomized thermal noise at that point.
Exactly. But when the active qLDPC protocol is engaged, utilizing the local memristors to track the syndromes and the FETs to apply immediate localized voltage corrections, the system stabilizes.
The logical fidelity plateaus at 99.64% and holds.
The error cascade is entirely suppressed without a single piece of data ever leaving the carbon matrix.
From an engineering perspective, a zero-fab, self-correcting monolithic carbon processor sounds like a 50-year timeline.
It really does, which makes their proposed manufacturing roadmap seem almost absurd at first glance.
Yeah, they outline an accelerated 14-day R&D roadmap to produce a working proof-of-concept prototype.
The idea of going from raw biological precursors to a functional quantum computer in 2 weeks requires a complete departure from traditional lithography.
Traditional semiconductor fabrication relying on extreme ultraviolet lithography, chemical etching, masking, and deposition is incredibly slow and requires billion-dollar clean rooms.
The authors propose bypassing lithography entirely in favor of maskless single-step femtosecond laser direct writing, or FSLDW.
And the process starts with a simple wet chemistry setup.
Which is where things get slightly surreal. You take a precursor. The paper specifically notes pre-treated hemoglobin powder or a graphene oxide dispersion.
Wait, hemoglobin?
Right. Hemoglobin as a quantum precursor is a wild thought, but it highlights the carbon-rich biological nature of the approach.
Wow, okay, so you take that and you freeze-dry it into a hydrogel monolith using basic molds.
Exactly. Once they have the hydrogel, they hit it with a macro-scale CO2 or fiber laser to pyrolyze it. This bakes out the non-carbon elements and leaves the highly porous, super-elastic, graphitic aerogel scaffold.
So that forms the raw canvas.
Right.
And the precision work is done by the femtosecond laser. We're looking at a 780 nanometer wavelength laser pulsing at 100 to 500 femtoseconds, drawing 1 to 3 watts of power.
The beam is focused to a submicron focal point and scanned volumetrically through the 3D aerogel guided by a CAD file, and the laser is effectively multitasking.
Depending on the focal intensity and the scan speed, the same laser pulse performs 3 distinct operations simultaneously.
First, through nonlinear multiphoton absorption, it ablates the local structure to nucleate the 3 to 5 nanometer graphene quantum dots.
Second, by slightly adjusting the pulse parameters on the fly, it graphitizes the surrounding pore walls, converting them into the highly conductive nanoribbons that serve as the electrostatic gates.
And third, on the periphery of the matrix, it uses varied ablation thresholds to write the channel layers and dielectric gaps for the classical graphene FETs and memristors.
It is essentially 3D printing a quantum computer from the inside out in one continuous scan.
Which sounds impossible, but the critical mechanism that makes this feasible without a mask is the real-time, closed-loop feedback.
Right. As the femtosecond laser ablates the carbon to form the quantum dots, the plasma plume and the dots themselves emit a specific blue photoluminescence.
By catching that luminescent signature with a spectrometer in real time, the control software can analyze the precise size and band gap of the quantum dot as it is being formed.
So if the dot is growing too large, say trending towards 6 nanometers instead of 4, the system instantly throttles the laser power.
This closed-loop photoluminescence monitoring guarantees the exact uniformity required to maintain the specific spin valley parameters across the lattice.
While a 14-day sprint seems exceptionally bold, we have to recognize that the roadmap is entirely focused on integration, not invention.
That's the crucial distinction, I think. Femtosecond laser direct writing in porous matrices is an established technique. The thermal isolation properties of aerogels are well documented. Bilayer graphene coherence has been demonstrated in isolated lab environments.
Right. The authors are not attempting to discover new physics. They are attempting a radical synthesis of existing 2026 material science capabilities to build a 4 to 8 qubit proof of concept.
And if the proof of concept holds, the scaling model bypasses semiconductor foundries entirely.
They outline a transition to roll-to-roll continuous manufacturing, feeding flexible precursor tapes through a continuous pyrolysis and femtosecond writing line,
targeting a density of 1 million qubits per square centimeter.
The ultimate goal being a flexible macroscopic quantum tape that, due to the extreme thermal isolation of the aerogel and the topological protection of the Kramer's pairs, operates increasingly closer to room temperature.
It is an absolute masterclass in lateral thinking applied to hardware design. But just as you, the listener, wrap your head around the mechanics of this continuous, information-dense, discrete carbon lattice, the white paper executes a conceptual pivot that shifts the scale from the nanometer to the cosmological.
Yeah, this is where it gets really mind-bending. The authors transition from proposing a machine that processes information on a discrete lattice to proposing that the universe itself is a machine processing information on a discrete lattice.
This requires a fundamental shift in how we visualize reality. For the past century, physics has largely treated space-time as a smooth, continuous manifold.
The classic rubber sheet of general relativity, where mass tells space how to curve and space tells mass how to move.
Exactly. But general relativity is fundamentally incompatible with quantum mechanics. Quantum mechanics is discrete. It deals with quanta, specific packets of energy, and distinct states.
And the search for a theory of quantum gravity has been the attempt to reconcile the smooth geometry of spacetime with the chunky, discrete nature of quantum reality.
The quantum lattice cosmology approaches this by discarding the smooth manifold entirely. They propose a kinematic foundation where spacetime at the Planck scale is a discrete network of interconnected nodes.
Mathematically, it is a complex graph defined as G equals V.
where V represents the nodes, or the fundamental quanta of space, and E represents the edges, the mathematical connections or entanglement links between those nodes.
It maps perfectly to the architectural structure of their Aerogel quantum computer.
It really does. The entire state of the universe, which they denote as psi subscript lattice, is not defined by particles floating in a void. It is defined exclusively by entanglement and information density across this grid.
They assign a local variable to every node, rho subscript I, representing the local information density.
If the universe is just a vast network of nodes passing information, we have to redefine what physical stuff actually is. In classical physics, we treat mass as an intrinsic property of a particle, often derived from interactions with the Higgs field.
But in this information-centric cosmology, mass is completely redefined.
Right. Mass is equated to von Neumann entropy, represented by S.
It is fundamentally a measure of localized complexity.
To visualize this, I try to step away from the traditional bowling ball on a mattress metaphor for mass, because it relies on gravity to explain gravity.
That was a bit circular, yeah.
Instead, consider a massive data center. Empty space in this model is like a row of idle servers. The network is quiet, connections are uniform, information flows perfectly straight and unimpeded.
A low entropy, low complexity state.
Now imagine a massive algorithm, millions of complex and tangled routing requests is suddenly dumped onto one specific server cluster. The data becomes highly tangled, localized, and incredibly dense.
That specific cluster becomes a bottleneck of sheer complexity.
Right. In the framework of this white paper, that localized knot of dense algorithmic complexity actually is mass.
And this redefinition directly challenges our understanding of gravity. If mass is just a localized region of high computational complexity on the cosmic graph, why do objects attract one another?
To answer that, the authors introduce a mathematical operator called the graph Laplacian, denoted as L equals D minus A.
The graph Laplacian is a staple in network theory and computer science. It essentially measures how much a specific node in a network differs from its immediate neighbors.
So in the context of this cosmological model, it calculates the tension or the routing delay across the discrete space-time fabric.
Going back to our data center analogy, you have that one server cluster bogged down with massive computational complexity, our mass.
Right.
Because that node is processing so much information, any new data trying to route through that specific area experiences a delay, an algorithmic drag.
The graph Laplacian mathematically dictates how that localized drag affects the surrounding network. It solves the discrete Poisson equation, defined in the text as L times phi equals F.
Let's ground those variables. The F term is the source vector. It represents the actual location and density of our algorithmic knot, or von Neumann entropy.
And the phi term is the resulting emergent field.
So the equation states that the structural tension of the network, L, acting to route around the field, phi, is entirely dictated by the local concentration of information, F.
When the local network slows down to process the mass knot, the path of any incoming information is naturally bent toward it, simply because it takes longer to process through the dense area.
That algorithmic delay, that bending of the information pathway, is what we perceive in the macro world as gravitational attraction.
So gravity is not a fundamental force pulling objects together.
Right.
It is an emergent phenomenon. It is the geometric consequence of the information lattice structurally adjusting to manage a highly dense gradient of von Neumann entropy.
And the authors validate this math with a simulated 2D grid looking at the emergent gravitational potential. They model a 31 by 31 discrete graph. They place a high concentration of information, the source vector F, at the center node.
And the graph Laplacian beautifully calculates the resulting tension, producing a smooth downward deformation in the potential field.
A mathematically perfect gravity well emerges purely from discrete network routing rules.
This provides a brilliant quantum classical bridge. This is the holy grail of modern physics, explaining how the chunky quantum world scales up to the smooth classical world.
Right. In the near field, at the micro scale of individual nodes, the universe is choppy. The graph Laplacian calculates discrete, jagged jumps from one node to the next.
This represents the domain of quantum gravity.
But as you zoom out to the far field, Observing trillions of nodes simultaneously, those individual discrete calculations statistically smooth out.
The algorithmic delay across the massive network perfectly converges into the classical inverse square law of general relativity, where gravity falls off proportionally to the square of the distance.
The discrete math of the quantum world naturally builds the smooth curves of Einstein's macroscopic universe, simply through the law of large numbers applied to a network topology.
It's stunning. But networks have bandwidth limits, right?
Exactly. If mass is just dense information and gravity is the network straining to process it, what happens when you overload the system?
What happens when you pack more von Neumann entropy into a local node than the network can mathematically distribute?
The framework addresses this by invoking the Bekenstein bound.
The source material doesn't provide the exact thermodynamic equation for the bound, but in physics, the Bekenstein bound represents the absolute maximum amount of information that can be contained within a finite region of space before the laws of thermodynamics collapse.
In the language of the quantum lattice, it is the threshold of Laplacian saturation.
The discrete connections, the edges of the graph, can only carry a finite amount of tension.
Right. If the local information density, rho subscript I, exceeds the Bekenstein bound, the graph Laplacian cannot mathematically balance the equation. The localized entropy gradient is too steep for the surrounding network to distribute.
The algorithmic routing completely fails.
And the result is a structural breakdown of the local topology. The white paper calls this lattice collapse.
The connections snap, the nodes become infinitely isolated, and the local space-time fabric ceases to function as part of the broader universe.
And from an outside perspective, this lattice collapse is what we observe as a physical singularity.
A black hole?
Or, if you reverse the timeline and look at the origin of the universe, the Big Bang.
The model provides a purely geometric, information-theoretic explanation for singularities. They aren't infinitely dense points of matter breaking the laws of physics.
They are simply localized regions where the information density of reality exceeded the processing bandwidth of the cosmic lattice.
It replaces the infinite absurdities of classical black holes with a clean mathematical limit on network capacity.
It is an incredibly elegant synthesis. But as with all grand unified theories, we have to pause and look at the empirical reality.
Yeah, we have to be grounded here. The authors explicitly state that this cosmological framework is a mathematical proof of concept.
It is entirely theoretical at this stage.
There are no benchtop experiments proving that space-time is a discrete graph, nor are there astronomical observations that can definitively confirm the graph Laplacian is driving galactic dynamics.
The authors rely on the mathematical elegance of the model and propose that future high-fidelity simulations might validate the specific gravitational scaling laws they predict.
The physics community has seen many beautiful mathematical frameworks, string theory being the most prominent, that struggle to produce falsifiable real-world predictions.
True, but the fact that this cosmological model is fundamentally tied to a physical engineering roadmap makes it uniquely fascinating.
That's the kicker. This white paper isn't just floating in the realm of pure theory, it is grounded in the literal construction of a device.
The physical quantum lattice computer and the theoretical quantum lattice universe are governed by the exact same discrete mathematical rules.
Which brings us to the profound realization at the heart of this deep dive. The team behind this paper is actively pushing through their 14-day fabrication sprint.
They're using femtosecond lasers to carve precise arrays of graphene quantum dots into a monolithic carbon aerogel.
They're using local memristors to manage the tension and flow of information across a discrete 3D grid. They are meticulously engineering a localized environment that operates on the exact principles they believe govern space-time itself.
They are building the hardware to run the mathematics of reality.
If they succeed in building this zero-fab, all-carbon quantum processor, if they can scale it to millions of qubits per square centimeter, perfectly managing the von Neumann entropy of the data within, they're doing more than just revolutionizing computation.
They're instantiating a localized cosmos.
To leave you, the listener, with a final thought to mull over. If reality is a discrete lattice governed by information density, and we build our computers as a discrete lattice governed by information density, the line between computation and creation blurs. At what point does a simulation operating on the fundamental source code of reality become indistinguishable from the reality it was designed to model? Are they building a better calculator, or are they, node by node, carving a new universe out of a flawless block of carbon? Keep questioning the architecture.